Watch what happens inside a conductor, where a lattice of positive ions is neutralized by mobile and constantly moving electrons.
An electric field passing through a conductor forces the electrons to flow until they pile up at the surface, repelling the motion of further electrons. But that means the electric field inside any conductor becomes equal to zero when electrostatic equilibrium is established. Therefore, a closed surface inside the conductor has no flux through it. So the net charge inside must be zero. But there can be charge at the surface, and no matter what's outside, the surface charge makes the field inside equal to zero.
And since all the action's at the surface, a metal box of any sort, even a flimsy screen-covered cage, can keep out an electric field. That fact can be demonstrated with this device, a gold leaf electroscope. Notice how it responds to the field of an electric charge. Notice, too, that even when an electroscope's inside the cage, it reacts in the same fashion. However, when the box is enclosed, an electric field can't enter to disturb the gold leaf. Any metal box can do it. And to this day, any metal box that does do it is called a Faraday cage. Of course, not every Faraday cage was designed to protect its contents from electric fields. The steel girders of a bridge or the scaffolding of a tunnel probably couldn't care less about keeping electric fields at bay. But they do a pretty effective job of it nonetheless. Why? Because radio waves are a kind of disturbance in the electric field. And because whether it's a bridge, a tunnel, or merely the enclosed container that its name implies, a Faraday cage isn't a great place to get good reception. Outside again, the reception's fine. In any case, while cars can go just about anywhere, where can the lines of a uniform sphere of charge go?
An extended region of charge might consist of many point charges in space. But if it's symmetrical, the electric field has only one place to go, and that's outward. According to Gauss's law, the flux through a closed surface outside depends only on the total charge. And if the charged region is a sphere, the size makes no difference.
So, in other words, the electric field outside is the same, whether the charge is uniformly distributed in a sphere or concentrated at a point at the center. And by the same reasoning, because it depends only on its inverse square nature, the gravitational force of the Earth is the same as if all its mass were concentrated at the center. Isaac Newton had to use his most powerful mathematics to prove that point, which may have contributed to the 20-year delay in the publication of the Principia. But with the help of Michael Faraday's vivid mental picture, the reason behind the idea can be perceived and completely grasped without any mathematics whatsoever. Not that mathematics wouldn't apply. After all, in the end, the best scientific expression of Faraday's ideas, indeed the ultimate triumph of the electromagnetic field theory, would be the mathematical expression of James Clerk Maxwell. Faraday would come to admire Maxwell, and quite properly, the admiration would go both ways. Responding to a letter from Faraday, Maxwell wrote, "You are the first person in whom the idea of bodies acting at a distance has arisen as a principle to be actually believed in. Nothing is clearer than your descriptions. You seem to see the lines of force curving round obstacles and driving plumb at conductors, and swerving towards certain directions in crystals, and carrying with them everywhere the same amount of attractive power spread wider or denser as the lines widen or contract." And thinking of gravity as well as electricity, Maxwell concluded, "Your lines of force can weave a web across the sky and lead the stars in their courses."